you so much. So I will take an approach which is quite complementary to what was already presented by Hall when he showed us the ecosystem of the features that arrive and grow up around and based on LLVM. And the previous talk where we also had the a brand new feature coming in. So this time, let's see what precisely what we are missing. So in a perfect and ideal world, the compilers just do the right thing. They find the optimum of all the metrics that we want to follow, whether it's performance, code size, energy, or any combination of the above. They are obviously bug-free. They preserve all the necessary debug traceability information as mentioned in the questions just minutes ago. And they run fast. Well, we already got that. And in this ideal world, basically compiler engineers are out of their jobs because everything just runs perfectly. Well, in reality, it's not exactly like that. And we're facing pretty complex software systems. So 3-4 million lines of code. That's about 1,000 to 1,300 man years of effort. About 250 successive passes, even in just the LLVM optimizer. There are quite some correctness bugs over there as well, because even if we assume the code is at the space flight or nuclear power plant quality levels, that's about 1 bug per million lines of code. So we have 4 bugs, right? And the real challenge actually is in the non-functional aspects of compilers, which is basically performance or the any other metrics of interest. So correctness issues are normally addressed by quality assurance. So the standard flows, actually the figures for the size of the compilers don't mention the size of test suites. So that's another good couple million lines of code that had to be added there. So we have code reviews, we have unit testing, we have regression tests, the regression test campaigns run, say, on a nightly or continuous basis. But that doesn't really handle the non-functional aspects. So let's actually, if we look at who are the stakeholders of improving a compiler, well, there are actually 3 big groups of people interested in getting a better infrastructure or getting the best out of the infrastructure. And those are compiler developers, obviously, compiler users, so basically those who really put code on machines to get the HPC rolling. And then people who have to manage all this, and they all have different perspectives, different aims, and a different process that they follow in achieving the aims that they have. So from the compiler developer point of view, there's a one compiler and plenty of configurations you have to deal with. I already mentioned that really the objective is to have the compiler correct, flexible, efficient, and of course the standard procedures of bug fixing, tuning, and continuous improvement. Well, those are the bases, really. For compiler users, well, there's a class of applications, one compiler, and usually one kind of HPC machine, or not necessarily HPC, actually. The same holds for embedded applications. Obviously, in an HPC perspective, what you really want to have is performance, once again, performance, and then possibly the energy bill at the end, which should be reduced. And to achieve those aims, well, step one is getting code running correctly, but then determine best settings and maybe adapt to shortcomings of the tooling where it doesn't do a perfect match between your application and actually the generated code issued from your application and the target platform. And of course, to manage all that at the compute center level or higher, you essentially want to get a return on investment from the assets you have, whether they are people, hardware, or software. And well, objective number one is get the shortest possible lead time to get your new application deployed, and then get the, again, performance and throughput on your system to run as many jobs as possible on the resources you manage. And obviously, you need to optimize costs and improve the efficiency of stuff and all your resources. So, well, in the compiler, from the compiler perspective, there is one important part in the flow that's actually a critical path for any of your compilation flows. And essentially, that's the common optimizer, which is not big compared to the other parts of the of a compiler project. It's actually relatively small meaning 200,000 lines of code. That's basically something like 8 times smaller than the front ends put together, or 1/3 of the backends. But this is the part which has to be traversed by each and every piece of code that you compile. So if you want to spot the opportunities, whether missed or future, inside those 200 lines, 1,000 lines of code, well, you can't really do visual inspection. It's a little bit too big. So an alternative is to use exhaustive search, but that doesn't work on a daily basis. Say if you take just 60 something transformation passes that are applied by the LLVM optimizer at -03, and that's 2 power 65 possible combinations of enabling, disabling passes. And then you have all the parameters. And then you can think about pass reordering, which is not that easy. It's basically, it builds up to 10 power 100 combinations easily. So a better way probably is to divide the problem and start to examine the situation at the point where you divide. So what you really want is something that's portable across successive releases of the compiler, across the targets, and also works with different applications, something that's agile in terms of the daily development flow. So if you spot something, spot it early and take it, take advantage of the knowledge as soon as possible. The versatility is also very important to help finding problems in the optimizer that span multiple use cases or multiple targets, for example. And one very important last property that we are seeking is actually the insight that you get from finding a problem, being able to isolate the root cause of a deficiency. So if I take an analogy with a big train, which has 270 cars, just like the optimizer has 270 passes plus, maybe it's just a way of chunking this into pieces and checking if at a specific point where you look, things are okay, or conversely, something has gone wrong. This is a nice sequential pattern, which can be applied to just anything operating in sequence. It's pretty agile, just linear complexity. It's versatile. Actually, here we can consider that any white car is our target point, and we just look at the situation at every white car. even at the end of the train at the horizon. So the other important thing is, as soon as you spotted a problem, you know where it is. So the question is, can we automate that? If we look at just the processing flow of an optimizer, it has analysis phases, or passes actually, followed by a transformation, which changes the behavior of code or its structure. And then again, a bunch of analysis, another transformation, etc., etc. So what if for each and every benchmark of interest, and it can be totally different for different users, what if you compile the successive partially transformed versions of that benchmark and check if we find defects or improvements? So essentially, we need to know the passes, we need to know the full sequence of the passes, and if we apply that sequence of optimizations, we obtain the equivalent of -02, -03, etc. And then we can use this full transformation sequence as a baseline and compare the partial builds of our benchmark against the baseline to figure out whether there's improvement or degradation. So this means we run a benchmark iteratively. If I will build and run a benchmark iteratively until the first, second, third, etc. transformation pass, we check the result of the correct operation of the code that was produced by such a sequence of analysis and transformations. And then we have three informations that we can already use. One is the correctness of the code. If it's not correct, there might be an optimizer bug, and most likely is. Then an improvement in performance over the baseline means actually we did better than the baseline, the -03, let's say. Then if we see a degradation between two successive cutoff points, we have an indication that something potentially counterproductive may have happened. So this is an approach that can be used in day-to-day development flow under certain conditions. You need to have a set of representative benchmarks, and those are actually the benchmarks for you, for your specific use case or use cases. Or in the case, it's quote, quote, easy for those who build actually who compile applications of a given class for a given class of architectures. It's more difficult for a compiler. What kind of benchmarks do you use as a developer of LLVM as such? Then clearly you need the processing time and the processing resources to generate all the different variants of the code and run them. You need storage space to store those variants, and then you need to be able to run and measure those, which is not always trivial, because sometimes you really need a special test bed to perform the measurements, for example, for embedded applications. So once you have the different variants, but you have satisfied the prerequisites, you have the space, you have the resources, etc., you can really build the different variants, save them in intermediate files, run the individual executables, and collect runtime data, whatever they are. But you definitely want the output correctness information. You need your metric that you want to improve, and you may want traces from execution and whatever other information. So then you assemble all that data and start looking into changes. How do you deviate from the baseline? In which direction? Better, worse? And how you change from one prefix sequence of transformations to the other. If you add a new transformation, do you improve? Do you worsen? And then, well, step 3, which is becomes mostly manual, if not highly manual, is analyze the trends and patterns that occur in the changes that you observed. And then you have to act upon that. So let's take a condensed report from running, well, an oldish version of LLVM, I agree, on just plain i5 platform against a baseline, which is -03. Well, if you sort the information about your configurations by just the best execution time reduction and by the transformation, which was the the last good one and the first degrading one, you might actually get patterns which are recurring across your benchmark base. And here in this set of measurements, which was run actually on collective knowledge and collective mind benchmarks, simplify CFG, actually, the very first application of it, has caused quite significant trouble. So if we look more carefully at just the behavior for one of actually the most striking case, we can see that between instruction combine and simplify CFG transformation passes, well, the performance went, got degraded dramatically. So for a compiler developer, a natural reaction there is to start looking into what caused the degradation, what was the structure of the code before, what's the structure of the code after. And in this specific case, it appeared that there were performance critical loops which had highly unbalanced if statements inside. And those statements were aggressively converted. So actually the short path taken most of the time was extended to the longest of the true and false paths. You can use this approach to analyze interactions between transformations. So on A53, we observed some interesting behaviors linked to loop transformations. Essentially, loop rotating improved performance on 2 benchmarks in a very nice way. But then suddenly, when applying loop unrolling, we realized that, well, both the code size improvement and the execution time improvement was lost for the first graph. For the second graph, actually we had a very good, we had an improvement in performance which was preserved till the end of the compilation, meaning that when reaching the -03 sequence of transformations, we actually got better. So that's quite counterintuitive, but what happened actually here was that the loop unrolling was not applied in this, exactly at the same way as a -03. We had actually a different parameter threshold for unrolling that resulted from an artifact of our way of assembling the transformations to be performed. And simply the backend was running at -00 instead of -03. When you take the findings from this analysis phase, well, they can serve several purposes. You can use them to detect, identify, and eliminate bugs in the compiler, or actually in the optimizer. Those bugs can touch on correctness, on performance, and on other metrics, maybe more relevant sometimes to the embedded community, but things like code size can have a serious influence on your cache behavior in HPC, for example. The good thing also is that you get the information you assemble there can be compared across targets, and this will pinpoint shortcomings which are specific to a target, or conversely apply to several targets at the same time. And obviously a different use, as I mentioned for the previous slide, is to find issues in heuristics, and which are of the compiler, and the thresholds of various transformation parameters, which you can actually adapt towards specific workloads or towards specific target features. That might actually influence the default thresholds that will be used for an improved version of the compiler. A question that's often asked is, how does this, say, daily routine approach relate to machine learning and to machine learning based methods of compiler tuning? So clearly we have a whole set of data, a large set of data that has to be processed and understood. Here machine learning can be of enormous help to detect patterns in the campaign reports, and also in classifying and prioritizing those patterns. So we've seen with an example report that there were clusters of similarly behaving transformations and transformation sequences. So machine learning there will be of enormous help. On the machine learning tuning side, well, our approach has a different goal. It's truly aimed at providing feedback to compiler developers to improve the compiler, to spot the deficiencies or unlock potentials. The goal is not to find the absolute optimum for a given class of programs, input data sets, and targets. So we don't really compete. We actually have one big shortcoming compared to machine learning tuning, which is that we deliberately constrain our search space. And that means we may miss a lot of gains. On the other hand, we improve in terms of performance for day-to-day usability, and we have ClearBox approach where the findings actually are directly related to the optimizer source code. And in addition, we provide actually a general debugging aid for the operation of the compiler. So where that can take us further? Well, first thing is in the field support to LLVM power users, helping with the tuning of the compiler or tuning a set of applications plus compiler to a given target. If there is interest and funding, we can clearly think about automating a hidden potential tracking service, which can run and report on a daily basis where we see where there are degradations or hidden opportunities in the optimizer. This same approach can be applied with quite some difficulty at times to other compilers. For example, GCC. What you really need is a pass control interface to stop processing or disable parts of processing in the compiler, in the optimization flow. And finally, there are uses of the method that can help, for example, speeding up the tuning of support for a new target, which is not fully understood, and its interactions with the optimizer are not fully understood, and that can be, for example, applied to RISC-V. if I'm to give a take-home message here, it's first that there are benefits to all categories of stakeholders of compiler development. For compiler developers, obviously, this is a direct aid in figuring out what features, or actually what potential was missed in the compiler, where it can be tapped and in which ways. Obviously, the bugs, whether functional or non-functional, can be caught almost in flight during the optimization flow, early and precisely. And the turnaround time in improving the compiler gets significantly shortened because you identify even specific modules in the transformation library which are at fault. So for compiler users, essentially, it's if you can get 25% hidden in a compiler somewhere, this is enormous. If you get 5%, it's a lot. This is for the improving the result of a compilation, but there's also an interaction with the compiler developers, where this approach could actually help probably giving a very precise and very targeted feedback to compiler developers about, look, here something that doesn't work right, and there's a hidden opportunity. And finally, from a management point of management of compilers, management of application deployment, if you can get the couple percentage points here and there, it's already a lot. And when the different gains are summed up, well, they actually can result in significant cost reductions in running an HPC system, both from applications side, application throughput, actually lead time to application deployment, and then application throughput and the bill of energy at the end of the day. So this is where I call for questions. But also, the slides will be shared, no problem there, and they will have pointers to further reading. There's a journal paper about this method that's just about to be published, and there's an earlier paper about tuning applications and tuning the energy and performance as a multi-criterion optimization. And the work was supported by a TeamPlay project funded by the EU. Thank you so much.
Thank you very much.